In general, we can explain the electron domain geometry that we predict using VSEPR by invoking the following hybridization schemes. Okay, so for steric number of 2, as we've seen earlier, we have to invoke an sp hybridization. So if you hybridize an s orbital and a p orbital, that gives you 2 hybrid orbitals, and those are all sp, both of those are sp orbitals that are going to be directed 180 degrees apart. Okay, so that would explain the linear geometry around a central atom that has 2 groups of electrons sticking out of it. So the 2 sigma bonds that will come that atom will be forming will be using an sp hybrid to overlap with the neighboring atom. If the steric number is 3, then in order to get that 120-degree bond angles of the sigma bonds sticking out of the atom, you're going to need an sp2 hybridization. That means you have to hybridize an s orbital with 2 of the p orbitals. And that will give you 3 hybrid orbitals, and those hybrid orbitals, we call them sp2 hybrids. And similarly, if you want to account for the tetrahedral arrangement of 4 electron domains sticking out of an atom, then you're going to have to hybridize an s orbital with 3 p orbitals. Okay, and that should give you 4 sp3 hybrids. So each of these orbitals, for example, in methane, okay, CH4, if you remember, that's a tetrahedral structure. The geometry is tetrahedral. You have 4 groups, okay, 4. So you have 4 single bonds sticking out of your carbon atom. So you have 4 sigma bonds there, 4 CH bonds. Each one of those is a sigma bond. The hybridization, the hybridized orbital that your carbon atom is using to create those sigma bonds is an sp3 hybrid. Okay, so the hybrid, each of those 4 bonds uses an sp3 hybrid from the carbon atom. For steric number 5, you recall, to get, if you have a steric number of 5, you'll have to invoke, the geometry is trigonal bipyramidal. You have three pairs of three electron domains oriented 120 degrees apart, right? Sorry, 120 degrees apart, and then those are your equatorial groups, and then you have 2 axial groups. You can imagine those as pointing towards the North Pole and the South Pole. So here's your axial group. This is an axial group down here, and you have 3 equatorial groups. For that, you're going to need to hybridize 5 orbitals, and those 5 orbitals are an s orbital, 3 p orbitals, and a d orbital. Okay, and so remember we said before that if you have atoms in row number 3 or below, they can have more than an octet. This is one case where you can have an atom having more than an octet. In this case, you can have like 10 electrons surround 10 valence electrons around the atom. And the reason it can do that is because you can now avail of those available p orbitals. So we hybridize one of the d orbitals with an s and the 3 p orbitals. That will allow you to get 5 hybrid orbitals, and we call those hybrid orbitals sp3d. And finally, if you have a steric number of 6, you're going to need to hybridize an s orbital, 3 p orbitals, and 2 d orbitals. So the hybridization is sp3d2. Okay, so let's apply those to this question right here. According to valence bond method, what hybrid orbitals would be involved in the overlap between, what hybrid orbitals will overlap between the carbon and nitrogen in this structure for urea? So this is urea. So this carbon to nitrogen bond, what would be the hybrid orbitals involved in the overlap? Let's take a look at carbon. Carbon, as a steric number for carbon, is 3, right? There's 3 groups sticking out of the carbon, so we know that this should be 120 degrees, that should be 120 degrees, and that should be 120 degrees. 3 groups sticking out of the carbon atom should be at 120 degrees apart. So the hybridization you're going to need here is sp2. So the carbon will have to use an sp2, and it's going to overlap with What hybrid for nitrogen? Look at nitrogen right here. There's 1, 2, 3, 4. 4 groups of electrons sticking out of your nitrogen. So the steric number for your nitrogen is 4. That's a tetrahedral electron domain geometry. So the hybridization that you're going to need for the nitrogen is an sp3. Okay? So we say that the carbon to nitrogen bond here is an sp2 to sp3 overlap.